So we're going to look at logarithms now. We finished exponential. We're going into logs. Which means next week you're going to have an exponential and log test. Haven't decided yet. So we're going to look at 2 to the x, which we did yesterday. So if we have 2 to the, if we plug it into this table, 2 to the negative 3 is 1/8. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. So we're literally just plugging in the x values and getting our y's, right? Or we could go to our table of values. Now the inverses of any equation, what is the definition of an inverse? You guys have done this before. No, that's f of x. So you have inverses on your test tomorrow, so that's scary. The inverses are when your x's and y's switch and you solve for y every single time. They reflect in the identity line, which is y equals x. So if we want the inverse points, we just flip our x's and y's. So we're going to get 1/8 and negative 3, 1/4 and negative 2, 1/2 and negative 1, 1 and 0, 2 and 1, 4 and 2, 8 and 3, 16 and 4. So literally our x's and y's switch, that's it. So if we graph the 2 to the x graph, we have an asymptote on the x-axis, so that's at y equals 0. We have coordinates at negative 3 and 1/8, so very close to the x-axis. Negative 2 1/4, negative 1 1/2, 0 and 1, 1 and 2, 2 and 4, 3 and 8. And then our line comes close to the asymptote, but doesn't touch it. And it runs up. From yesterday, what part of the equation gives me my asymptote? The y equals line, yes, but where do we get that from the equation? What can move it? The vertical translation. The vertical translation gives us the asymptote, correct? So what's our vertical translation on this? Y equals 2 to the x plus 0. So it's at 0, right? So the only thing that can move our asymptote is the vertical translation. And our range is always greater than 0, or the asymptote, unless we have a what? Deflection in the x-axis, which causes it to go down. It would be less than that asymptote, right? So now we're drawing the inverse of it. Okay, the inverse of this is 1/8 and negative 3. And then we have 1/4 and negative 2. And then 1/2 and negative 1. And then 1 and 0. And then 2 and 1. And then 4 and 2. 8 and 3. So we're getting closer and closer to the y-axis this time and curving, which makes sense because inverses reflect on the identity line 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. They reflect on the line y equals x. Did these reflect on the line y equals x? Yes. The graphs did. The asymptote of the purple graph is at y equals 0. What would the asymptote of the green graph be at? X equals 0. They flip. You're right. So I have a vertical asymptote at x equals 0. Do you agree? What you don't know is that's a log graph. Logs and exponential graphs are inverses of each other. So what is going to move this vertical asymptote at x equals 0? What's the only thing that's going to move it? If a vertical translation moves y equals 0, what's going to move this one? The horizontal translation, because you're moving it this way or this way, right? It's vertical, and you're moving it either to the left or the right. So the horizontal translation moves the log asymptote, or tells you where it is. So if it was like x plus 2 beside the log, it would move it to the left. And instead of it being greater than 0, our domain this time, right? It would be greater than 0. What would cause it to be less than 0? A reflection in the y. They're just inverses of each other. Okay? That's it. Does that make sense? So if we do the domain of the inverse, so this is going to be of the inverse. Sorry, we'll do, oh, I forgot. Still doing this. Great. So we'll do original. So y equals 2 to the x. And then we'll do inverse in green. So what's the domain of the exponential of the purple graph? It does this. XER, because there's arrows going this way and arrows going this way, right? Out to the left and to the right. So it's XER, or an interval notation, negative infinity, infinity. What's the range of this one? Y is greater than 0. Not equal to. So it's going to be 0 to infinity. What's my asymptote at? Is it a horizontal or vertical, the purple one? Is it a horizontal line or a vertical line? Horizontal asymptote at y equals 0. And how many I have no x-intercepts, right? But I have a y-intercept at 0, 1. So my green graph then, what is my domain? X is greater than 0. I have no graph in the negative zone of x, right? What did I tell you about inverses? The domain of the original is the range of the inverse, and the range of the original is the, look at this, x is greater than 0, y is greater than 0. They're inverses of each other. So the domain is XER of the purple, so the range is going to be YER. This one I have a horizontal asymptote at y equals 0, so the green one I have a vertical asymptote at x equals 0. This one I have no x-intercept, so for the green one I have no y-intercept. And my y-intercept is at 0, 1, so my x-intercept is at 1, 0. Inverses are just opposites of each other. So if you do get an inverse question tomorrow, if I gave you an equation or gave you a point, you would just flip it. If I gave you an equation like y equals, let's pretend, I know this has nothing to do with this, I'm just showing you because just in case. Say I gave you y equals x squared plus 3. Let's pretend it's that. and I wanted the inverse of it. If I want the inverse of the equation, I literally have to find the inverse of the equation. But what if I want the inverse of the domain? I would just get the range of this one, and it would be the domain, right? I could get the domain of this one, and it would be the range of my inverse. I don't actually have to draw this graph unless it asks me to draw the inverse graph or asks me to get the equation of the inverse. Yeah? Also remember that I often have wanted you to restrict, and this is a curriculum outcome, restrict the domain of a quadratic, correct? So that when you draw its inverse, it's actually a function. We restrict the domain of the quadratic. This quadratic has a vertex at 0, 3. So this graph is at 0, 3, and it goes like this. I never restrict my inverse. I always restrict my original for you, those of you who are still restricting your inverse. I restrict the domain of my original, never the inverse, the original. So do I even need to draw the inverse to restrict it? No. Where does this graph cut in half? X equals what? 0. So if you gave me a domain as x is greater than or equal to 0, or you gave me a domain as x is less than or equal to 0, both of those would restrict so that my inverse would draw half a graph. Because I need my inverse to draw only one arm. Because if it draws two arms, like this, and I draw a vertical line through it, it's not going to pass it, correct? So I restrict my original to have either this arm or this arm, so that when I draw it, I only have this arm or this arm. But I restrict my original quadratic. I do not restrict my inverse. I restrict the original domain. Do not restrict your inverse range. We do not do that. You restrict your original always. Okay? If we wanted to solve for the equation, if I wanted the actual inverse equation, I would swap my x's and y's and solve for y. So what would be the first thing I do? When I solve for an equation, I do reverse BEDMAS. So instead of brackets, multiplication, addition, subtraction, I do addition, subtraction, multiplication, division, brackets when I'm solving. So I'm going to subtract 3 first. So I get x minus 3 equals y squared, and what am I going to have to do? And when I square root, I have to remember to plus or minus. And I'd have f neg 1 of x equals plus or minus square root x minus 3. It's all remembering what inverses are about, right? So logs and exponentials are inverses of each other, complete inverses. We agree? Okay, that's a minus, even though it looks like a multiplication symbol. So we're going to look at this first. A logarithmic function is the inverse of an exponential function. We know that. For the function y equals 2x, the inverse is x equals 2y. In order to solve this inverse equation for y, we have to change it. We have to convert. So you need to memorize this. This is the same as this. And you'll actually just learn it. You won't end up memorizing it. You'll just remember where to put the stuff. But the reason why we want to be able to convert exponentials to logs is if I can't get a common base and I have a variable in my exponent, correct? What's the only way we've been able to solve them? y1, y2. So I say algebraically, you can't get common base. You use y1, y2, you're wrong. Okay? So we need to be able to use logs so that when we want to solve for a variable in the exponent, algebraically, that we actually can if we can't get common base. Okay? Inversely, you convert back to exponential from a log if you don't know the values beside the log or in the base. This is called the base of the log right here, this little b. If you have an x in here in the base or you have an x in beside the log, the only way you can solve those is if you convert to exponential. So they're like besties. You have to use them backwards and forwards, okay? This is the way I used to remember them so that I don't actually have to memorize formulas, because you don't have these on your formula sheet. The base of my log is the base of my exponent, right? This is the base of my exponent. This is the base of my log, right? Whatever's with it over here Whatever's with the base over here is not going to be with the base here. They swap. So if I put my bases correctly where they need to be, the n is with it here. So the n is going to be what it's equal to over here, and the x is what it's equal to, so it's going to become the exponent. We'll practice enough of these that literally you will just be able to do the changing. Memorizing the formulas is not as helpful. It's better to just understand what you need to change. Okay? We also need to have a 1 in front of the log here. Do you see there's the log? There's a 1 in front of it right now. We have to have a 1 in front of it in order to be able to change it to an exponent. If we don't have a 1 in front of it, we're going to have to do something, which we'll learn. Okay? So we have a to the b equals c. We want to write it in log form. So the first thing I do is I write log, and then I write the base. What's the base of my exponent over here? A. So it's below. It's down here. It's like subscript. It's not in line with the log. Okay? What's with the base here? What's with the base in the exponential? A b. So I'm not going to put the b beside the log, because what's with it over here can't be with it with the log. So what's not with it? C. So I'm going to put a c beside. And then it equals b. Now, it should equal the exponent. Why should it equal the exponent? Because that's what we're solving for. Right? So if we can't get common base, we're trying to get what the heck the exponent is equal to. So when you actually convert an exponential to a log, it equals the exponent. Life is good. Life is easy. Okay? So converting the other way, we have logs. We need to convert to exponential. So the base of my log becomes the base of my exponent. Right? What's with it right now? An a. So are we going to put the exponent as an a? No, we're going to put the exponent as equal to a. We're going to put the exponent as b, and then we're going to set it as equal to a. And then the next one, what's the base of the log? C. What's going to be the exponent? D. And it equals. We agree? So not too bad, as long as you remember that. I always put my base first, and then what's with it can't stay with it. So then you know what needs to go. Okay? So we're going to express these in logarithmic form. We're not going to solve them. We're just going to express them, and then we're going to keep going. So the base of my exponent is 6. So I'm going to get log base 6, not multiplied by 216. It's going to go beside the log, and it's going to be equal to the exponent, which is 3. It always equals the exponent. Now let's prove that this actually works. So we have log base 6 of 216. I'm going to show you how you can all type it in your calculator no matter what you have. And then if you have the newer ones, I'm going to show you an easy way. So in order to type this into your calculator, this here needs to equal 3, correct? That's what it says. So the way we type it into our calculator is you draw a line underneath here and you put a log with it. So you're going to write it as, in your calculator, as log 216, close the bracket, divided by log 6. And what do you get? 3. So everyone can do it that way, no matter what calculator you have. If you have the new calculators, you actually have a button that will pop that up for you, and you can just fill in the boxes. So you're going to press math. Try this out. You're going to press math, and then you're going to go down to log base. Some of you have the newer calculators but still don't have that. So you're going to press math, and you're going to go down to, I think it's B, but I can't remember. No, A, log base. And you hit enter, and then it pops up with little boxes, and you put the 6 in this little lower box and the 216 in the higher box. It gives you 3. If you have the older calculator, you do not have that option. So you're going to go math, and then down to A for most people. So, yeah. So if you could go math and you could arrow all the way down to A as well, right? then just hit enter too. Okay. So you get 3. If you don't have that button, you have to do the division. But everyone needs to remember the division because sometimes they give answers in that kind of form. And you're like, I don't even know how they got that because you have the log base button and you've never had to put it in this form. So that ones who don't have the log base button are ahead if they give it in this form because you'll always remember you have to do that. Whereas the other ones forget it because they have the log base button. Okay? We're not going to do the rest into our calculators, but we're going to convert them. So here we have the base of our exponent is 3. So the base of our log is 3. What's going to be beside it? 81, and it's going to equal 4. It equals the exponent. C, we have log base 2. What's beside it? 116. And this 1 over 16 is perfectly in line. Like if I put a ruler underneath it, it would be perfectly in line with the log, right? It's log 1 over 16 and then subscript 2, okay? And it equals -4. The value here and the value here both have to be positive. You can't put negatives in there, it will fight you. Your calculator will fight you. Okay, so we have log, the base of my exponent is 2x plus 4. What's beside it is going to be an a, and it's completely in line with log, and it equals -1. Okay? Now, why would they want you to convert? They're not going to say convert. They're not going to say convert the exponential to a log. They're going to give you an exponential that you can't solve by common base, and they'll ask you to solve it algebraically, right? So then you have to convert it to a log. Or they'll give you a log that's missing the value beside the log, or they're missing the value in the base, and the only way you can solve those is by converting to exponential. So they're not going to say convert to exponential or convert to log. You're going to need to know to do that. Okay? So we're going to express these in exponential form. So this is 5 to the 3 equals 125. This one is the base of my log, which is 4 to the -2 equals 1 over 16. The next thing to note is if the log doesn't have a base, it's base 10. So just the log button is actually just log base 10, okay? So in this case, it doesn't have a base. So you'd be like, imaginary base to the 3 equals 1,000, which makes no sense, right? So when it doesn't have a base, I instantly go in and put a 10 so that I remember to use it. So it's going to be 10 to the 3 equals 1,000, which is true. 10 to the 3 does equal 1,000. And then D is K to the X equals T. Okay, I want you to type log base 2 of 8 into your calculator. So if you don't have the math button, you're going to go log 8 divided by log 2. And what do you get? 3. Then log base 2, 4. Thank you. It's 2. Log base 2 of 2. 1. 0. -1. So you're seeing a pattern. Very good for you. Oh, yes, that as well. You don't need your calculator to answer these. And I'll explain why. What your calculator is doing is this is equal to x, is it not? It's equal to a variable, like we don't know what the heck it equals. Yeah? What you're actually doing in your head, your calculator's doing for you, is it's going 2 to what exponent is 8. So you don't even need your calculator when it's something nice. If it's like 1.735 and then 6 beside it, yeah, probably going to need your calculator because I don't know what 1.735 to what exponent is 8. I actually have no idea. It's crazy decimal. Okay? But these ones you can. So 2 to what exponent is 8? 3. 2 to what exponent is 4? 2. 2 to what exponent is 2? 1. 2 to what exponent is 1? 0. 2 to what exponent is a half? -1, because it would take that 2 to the -1 and flip it. And then 2 to the what is a quarter? -2. So we didn't need our calculator to actually do these. Our brains can. Okay? Try it out. Give me answers. So for log base 3 of 9, 3 to the what is 9? 2. So these ones you could get away with actually punching them in your calculator and getting an answer, right? But we need to know how to do all these things so that when they give us variables instead of numbers, we can actually figure them out. So 4 to the what is 16? 2. 5 to the what is 125? 3 to the what is 27? B to the what is 1? Not anything. 0. B to the what is B? 1. This is something to state. If I have log a to the 6, let's say, my answer is 6. Whatever your exponent is up here, if these two are the same, it's going to be 6. You'll see why when we use the power rule where we bring it in front. That's something to note, that if your base and the thing beside the log are the same, your answer is just the exponent. B to the 1 is B. So we went over how to type that into our calculator already. So this is where it's actually helpful. The rest we were just practicing random stuff. This is why we actually have to convert them to exponential. Okay? So we're not going to look at A and B for now. We're just going to look at E, G, and F. So E, we have, this is just something to note. If you get this, 5 log 5 to the 25. Type that into your calculator. So it's 5 to the exponent. And if you have the non-fancy calculators, you're going to be going 5 to the exponent log 25 divided by log 5. This equation is 5 log base 5, 25. So if you have the non-fancy calculators, you're typing it in like this. If you have the fancy calculators, you're just going 5 to the exponent, pull up your log, and type it in. What do you get for an answer? 25. So these are little things to remember. Here's another one to remember. So if you have log, oh sorry, base. Oh, forgot about the eraser thing. Awesome. Nope, it's not smart. Yeah. So if we have a log a to the b, so if your base of your exponent and the base of the log are the same, your answer is just b. Something to note. And we just proved that by 5 log 5 to the 25 is 25. F. We don't know the base. We can do this graphically. We're not going to, but we can do F graphically. Why? What have I told you this whole year? You can do y1, y2 when you have something equals something and you're only missing one variable. Is that the same thing here? Yeah. It's log x 64 equals 3. You have something equals something, you're missing one variable. You could y1, y2 it. However, if I say algebraically, you're hooped, because that is not algebraically. But could you do that on any question on the diploma if it was a multiple choice and you could maybe work it down? Sure. Do we want to bank on only that because they know how to write better multiple choice and numerics so that you can't do that? No, we don't want to bank on that method, okay? But we want it to be able, we can always check though. So if we're missing the base, which in this case we are, Do you see we're missing the base? There's a variable in the base. Convert to exponential, and you can solve it. Okay, that's what we're going to do. So we're going to convert to exponential, and we're going to solve it. Because you're copying it down? You're not. Okay, so we are going to make the base of our log be the base of our exponent, and then what? To the what? 3 equals 64. And then how do we solve? You can cube root it, but what did I also tell you could do? No, you wouldn't want to y1. If you y1, y2 here, why wouldn't you y1, y2 in the previous step? Times both sides by a third. Raise them both to the exponent of a third. Why would we do that? Because if we multiply 3 by a third, it's just x to the 1, which is what we want. Could we have cube rooted it? Absolutely. You could absolutely cube root it, and you get x equals the steps? No, you don't. We're missing what's beside the log in G, correct? If we're missing what's beside the log in G, or we're missing the base like we were in the previous one, we convert to exponential. That's it. So we're missing what's beside it. Convert to exponential. So we're going to get base 3 to the negative 4 equals x. If we're missing what's beside it, it's easy. The moment you convert it to exponential, you actually have an answer. So you're going to get x equals 1 over 81. Okay? Not too bad. So these are some little rules for you. If you have a to the m, your answer is just m. If you have log a, any base to the 1, it's 0, because a to any to 0 is 1. And when you have a to the x, which I wrote here just so you could see it better, it equals x. These are 3 rules that everyone forgets about. So I would write them down. I just wrote it here. This one, this third one, is just this with x's instead of b's. So I just rewrote it because it's super tiny. It's hard to read. So instead of writing this one, I would just write that one. Okay? You guys try these. So we don't know what's beside the x, okay? The fact that you're in 30-1 means you're not going to get often direct things where you can just plug into your calculator. You get ones where they'll exponent you out, so your calculator will be like, no, I'm not doing this. Because you guys need to know your exponential rules. That's what 30-1 is compared to 30. This unit is partially in 30-2, but it's not in the same depth, okay? So we know we're missing what's beside. If we're missing what's beside the log, we convert to exponential. That's what we should think instantly, correct? If we're missing what's beside the log or in the base, we convert to exponential. So we're going to get 4 to the 64 equals 4,096 times x. Then we know we're going to divide by 4,096. So what you might think is, none of those answers are there. Great. But you can make 4,096 be a base of 4. Is it 4 to the 6? Okay. So we go 4 to the 64 divided by 4 to the 6 equals x. Now remember this. When we have common base, you guys told me this. When we have two bases and they have exponents and we're multiplying, we add the exponents, correct? So if we have common base and we're dividing, what do we do with those exponents? Subtract. So we get x equals 4 to the 58. I actually like logs and exponentials because it's kind of like puzzles, like you're working through. I'm sure you'll have people agree. Okay, so 14, we're going to work with the first one. We don't know what x is, but if we can find out what x is, we can plug it in for x and solve for t, correct? X is stuck beside the log. If we don't know what the answer is beside the log or in the base, we convert to exponential. So our brain should just instantly think that. So we're going to get 2 to the 3 equals x. So x equals 8. Great. Now I can use the second one. Log 2 to the t equals 8. Now I'm missing what's beside the log again. What can I do? Convert to, which is exponential. So you get 2 to the 8 equals t. Is it 256? Okay. I wasn't sure if it was that or 512. 2 to the 9 must be 512. Okay. In 15, we don't know the base. When we don't know the base or what's beside the log, we convert to exponential. There's an extra step if you don't know the base. There's that extra step to solve. If you don't know what's beside it, it instantly gets that, right? This will just give us a separate step, but we still convert to exponential. So we're going to get b to the 2/3 equals 81. Then what did I tell you to do? Yeah, do the reciprocal of it. So 3 over 2. Because 3 over 2 times 2 over 3 is 1. So we're going to get b to the 729. B equals 729. I don't know why I said b equals. It's not. This is just the square root of 81, which is 9. Cubed is 729. Because the bottom here becomes the index. It looks way more complicated if you don't split it. No. Okay. 16. We have a split up here. So, I don't know, but it smells good, doesn't it? No. So, we're going to go a to the 4.5 equals b. When in doubt, convert to exponential, because I got nothing else to do with this, right? So I'm like, maybe exponential will help. So a to the 4.5 equals b, and a to the 3.7 equals c. That we agree with, correct? If you guys always remember that if you don't know what's beside the log or in the base, you convert to exponential, this is a super easy lesson. If you don't know that, you will sit and stare at it and go, I remember there was something, but I do not remember what that something is. And I will plug it into y1, y2, and I will get the answer, and I will try and work backwards, and she won't catch me. She will. She will. She's me. I will see it. It will happen. You could try it all the time. Don't. Just remember that if you're missing beside the base, or the base or beside the log, convert. And then it's easy. Okay? All right. So we know that b equals a to the 4.5, so we're going to put that in for b. So we have log base a, which is wonderful. Boom, boom. We know b is a to the 4.5, so we're going to replace it. We know c is a to the 3.7, so we're going to replace it. What do we do when we have common base? Just cross them off and say, yeah, something division. Subtract the exponents. So 4.5 minus 3.7. We still have log base a. And then we're going to have a to the what? Why do I not want it in a fraction, even though most of the time I love fractions? No, I like fractions. It says nearest tenth. It's a numeric response, right? So I'm going to go for the decimal because I read the question and it said nearest tenth in it. It's crazy. And so then we remember the rule. If these are the same, what does it equal? The exponent. You can never just write 0.8. the first box in the numeric response does not have a decimal bubble. If you're like, meh, then I'll just put the decimal in the box and not bubble anything. Remember, the machine only reads the bubbles. The machine doesn't care what you put in the boxes, actually. Why do you write in the boxes? Because all of a sudden the machine doesn't, like, you didn't shade properly, or your pencil, it doesn't like it, right? Then they'll boot it out and they'll be like, oh, they got nothing right. There must be something wrong. They'll look at it and they'll see that it's not reading it, or it'll error code it. Then they'll go in and look at your numbers and bubble it. So you need to have the numbers as like a backup, but the machine reads the bubbles. So if you're going decimal 8, but you don't have a bubble for the decimal, the machine is reading nothing, 8. Then I'm like, oh, I'm sure they just put it in wrong. No, they're not. The machine has no heart. It doesn't love you. It's a machine. So you're going to go 0, decimal 8, because the 2 boxes in the middle have decimal bubbles. Okay? If you can't bubble in your answer, it can't see your answer. Easy as that. Okay? Your bubbles need to match the answer you want the machine to read. Yeah? Some of you guys don't. All right. If it were me, I would save this for tomorrow night for homework and review tonight. No. The reason why I'm saying that is tomorrow you're writing a test, so you won't have homework. So I would just save this for homework. Okay? So I would start reviewing. Go over stuff.